So I'll call this transmit equalizer. We have a number of flip-flops, as many as we have taps in the equalizer, and this is clocked by a signal. This is clocked by a clock at the data rate, and we take the weighted summation using voltage controlled current sources and pass the resulting current to a load to get the equalized output. And this load can be, for instance, one of the terminations of a transmission line. The other side will also be terminated by the impedance of the transmission line. Okay. And because we are dealing with binary data, each of these transconductors can be switched current sources. Okay. That is, we use differential pairs to realize these. And if we have a certain tail current I naught, we can get a differential current which is either I naught or plus I naught or minus I naught based on the polarity of the input data. So let's look at some more details of this. Let's assume a 3-tap equalizer with one precursor tap and one postcursor tap. Okay. Then I'll have 3 differential pairs in parallel. So let's go and design this in a complete way. So let's say this is terminated by load resistances R and R. Let's say the middle has a tail current I naught, and the equalizer I want to realize has weights G minus 1, G0 and G1. So what will be these tail currents? This and this. So it's in the same ratio as the taps. Okay. So this current should be G minus 1. I am assuming that I'll apply the precursor voltage here, the delayed one here, and another delayed one here. Okay. So this could be V minus 1, V0 and V1. So V0 is delayed with respect to V minus 1 by 1 clock cycle, and V1 is delayed with respect to V0 by another clock cycle. And the tail current source in each tap is a function of the equalizer coefficient that you want to realize. What's that? Yeah, okay, that's right. So typically, we have the precursor and postcursor to be taps to be negative, so that we get a high frequency boost. So the polarity will be opposite to that of the cursor tap. So again, this is assumed to be the absolute value. G minus 1 by G0 is negative, but the current of course always flows downwards. The basic operation I assume is clear for this circuit. Okay. Now, first thing is we can use Nmos or Pmos transistors. Which one would we choose? Pmos. Okay, one answer is that you can choose Pmos so that you get voltages with respect to ground. Yeah, now the counter argument can be that it is differential, so its common mode value doesn't matter. But it is still true that Pmos gives you not a common mode voltage of 0, but a common mode voltage that is closer to 0. Okay. So what else? How would you decide between choosing Nmos, between Nmos or Pmos? What is this? What is the primary difference between Nmos and Pmos? Mobility is higher. So what is the consequence of that? Huh? So GMs will be greater for same currents. Okay. So does it make any difference to this circuit? Yeah, we can have smaller transistors for Nmos. Let's say you want the differential pairs to switch at a certain voltage, and you want to switch a certain amount of current. Then the size of Nmos transistors will be smaller than that of Pmos transistors. So why is this a concern? What is the capacitance, the input capacitance of the circuit will also be smaller. So you have to drive a smaller load, so Nmos is better. So typically you tend to use Nmos. Again, we go to all these techniques to work at higher and higher frequencies. So at the highest of frequencies, you do use Nmos. You can always use Pmos, but you use Nmos if frequency is a constraint. Okay. Use Nmos at high frequencies. Pmos, the common mode level is closer to ground. This is usually not a big issue, but If it is, then you can, that could be one reason to use Pmos. Huh? I don't know, depends on what is the receiver. If the receiver is such that it needs a low common mode voltage, perhaps it's an issue. So, I mean, this if it is constrained by the receiver. Okay. The other difference between Nmos and Pmos is that Pmos devices tend to have lower flicker noise, but that is usually not a concern in these applications. Okay. You are transmitting a large signal, so that small amount of noise usually doesn't bother you. And also you are concerned with this again, we are talking about broadband communication, so you are concerned with frequencies from low to very high. So the flicker noise forms a very small part of that noise. So what will be this common mode voltage? The output common mode voltage? It is VDD minus the sum of the currents times R divided by 2. Okay. So it's VDD minus I naught, the sum of these normalized coefficients. Yeah. So as the coefficients, as the values of coefficients G minus 1 and G1 increase, the common mode will keep dropping. So there is a limit to the size of coefficient that you can realize. If the common mode keeps on dropping, then basically you cannot have all these transistors in saturation region. So that will be an issue. So if you want to keep all transistors in saturation region, you have to limit the values of G minus 1 and G1. Okay. The alternative is to reduce the value of I naught itself. So let's say these, you have to realize large values of G minus 1 and G1, and if you have more taps, all of that, they all sum in an absolute sense, okay. You have to sum the absolute values of the normalized taps. Then you can reduce the value of I naught or reduce the value of R and keep the transistors in saturation region. What will be the disadvantage of that? Less. Why? Yeah, that could be one reason. Actually, even more importantly, the signal swing is less. Okay, you are sending out a smaller signal. So while discussing crosstalk, etc., we said that if you put the equalizer at the transmitter, of course, it won't amplify the crosstalk or the noise. But the problem is now, if you have this, if you have to realize a complicated equalizer, you can only transmit a small signal. So although you are not amplifying noise, you start off with a smaller signal. So the signal to noise ratio is still degraded in effect because of practical constraints. Okay. Yeah, it is also true that if you reduce the value of I naught, the charging rate can be less, but you can counter that by reducing the value of R. You don't have to reduce I naught, right? It's the product that you want to reduce if you want to raise the common mode voltage. But this gives you smaller swing. Okay. So essentially the signal that you get out, if I write the equation for the differential voltage that comes out, what is it? It's I naught R. So let's say the data is denoted by X, the X of n, okay, plus G1 by G naught, X of n minus 1, okay. It's just a 3-tap FIR filter. So I naught R appears both in the equation for the common mode as well as in the output signal. The output signal is directly proportional to I naught R. Okay. So the smaller swing will lead to, so this is the practical constraint that prevents you from having a very large number of taps or having taps which have very large magnitudes in the transmitter. You can do something, but that always comes with a price. That is, if you didn't have these taps, if you didn't have the equalizer, then I naught R by 2 had to be such that these transistors are in saturation. But then if you introduce the taps, the value of I naught R by 2 has to reduce. Okay. So, but then that means that the total signal also has reduced. Regardless, finally you will get the same signal, right? You are saying you will have, let's say, xn plus 1, xn plus 2, and this goes to some block. You sum the output currents and do this, and you take two such blocks and you take the output currents, sum that and pass it through this. Is that what you are saying? Yeah, but finally the current flowing through this depends on all of these things, however you generate it. Okay, let's see. If so the signal you want to get out is this plus x of n. It's assumed that x is binary data, g1 by g0 x n minus 1. Okay, and this is negative, and this is also negative. Okay, so let's say you produce this by passing some current through a resistor R. I don't really care what that is, but it is obtained by passing some current through a resistor R. In this case, it's actually through differentially through two resistors of equal value. But now this current source can only be in one direction. Okay, let me actually draw it the way it is, that is as current sinks. So it comes through some circuit like this, right? However you generate it. Now what does this current have to be? What does the tail current have to be in this case? No, this is the output signal. What should the tail current be? The total tail current that flows through this. Not just through the one differential pair, whether you realize it as one differential pair or many differential pairs, what should it be? That current cannot be, the current going in this direction cannot be less than 0, right? So what is the total current that is drawn at a minimum? If you want a signal of, let's say you want a signal swing of certain Ix, okay, and you have a class A amplifier, what is the bias that you need, bias current that you need to support this? Are you familiar with class A? And no, you're not? Okay, class A just refers to the fact that the signal swing is less than the bias current. Okay. Now, I have to get the signal out, and to do this, the total current has to be at least, sorry, these are 1, okay. So this will, you will see that this will be the case. So whether it comes out of one transistor or many transistors. So if you want to transmit a given signal swing, you will have to have this much current that is swinging. Okay. So in that case, you will just have to have so much current, which means that the common mode value will drop to the same value. See the largest, so let's say this is the output. When do you get the largest output? When this is all the way at VDD and this is all the way at its minimum value. Okay. What is the minimum value of this? When when this is plus 1, this is minus 1 and this is plus 1. Okay, because the taps are negative, that will add up to the most negative value. Or if you make it the opposite, if you make minus 1 plus 1 minus 1, it will be the other way. Okay. So what will be and that current has to flow into one of the branches. Okay. So I have something like this, and to get the maximum positive voltage, I have to have this as 0 current. I can have it as some other current, in which case it will only be worse. Okay. I can have this to be 0, and what should this be? This is basically I naught times this, right? Sum of the absolute values of coefficients. Now I can make both of the currents larger than this, in which case the common mode will only drop. Okay. So I can't really, whether I do it with a single differential pair or any number of differential pairs, I cannot avoid this. Simply because I have this much signal swing. Okay. The maximum value of this is this one, and the minimum value is just the negative of that. Okay. And this happens with the right combination of bits. When the coefficients times the bit has all add up, or all add up either in the positive or the negative direction. So that much current I have to accommodate. So to accommodate that much current, I have to drop certain voltage across these resistors. Okay. Is this clear? Okay. What else was here? Next thing is, how do you connect it to the transmission line, and that has some implications on the swing as well. So let's say we have the driver on this. I won't show the transistor level circuit. It's connected to a differential transmission line. A differential transmission line for our purposes now is just a pair of wires. Okay. So there is a wire here and another wire here, and you have termination on the other side as well. Where would you connect this to? The common point of the terminations. Where should you connect it? To the output common mode of. Okay, let's say I will connect it to some Vx. Okay, this is on the receiver side. This is our transmitter. Sorry, this is our transmitter, and this is the receiver. And let's say you have terminations, and that is terminated by some voltage Vx. Now, does Vx have any bearing on the design of the transmitter? Does it affect the transmitter in any way? When there is no signal, there can be current drawn from the, basically DC flowing through these resistors. That depends on the value of Vx, right? So essentially, if you look at the, are you guys all familiar with common mode and differential pictures? Yes or no? So you make the common mode equivalent circuit by, let's say you have a differential circuit and you have a line of symmetry, and common mode by definition means all the differential inputs of the differential circuit are tied together. They are tied to the same voltage. So I tie these two together, and if that happens because of circuit symmetry, these two will also be at the same voltage. So I can actually connect these two. So I can make a half circuit with essentially almost half the number of transistors. So if this is R, this becomes R by 2, and if each is W by L, this becomes twice W by L, and this current source remains the same. Whatever is in common mode remains the same, whatever is in differential gets folded over. Okay. So I can use this picture to analyze the common mode. What happens in the common mode? So this is the common mode picture of the transmitter, and the transmission line is just a wire for DC. What is the common mode picture of the receiver? It is a single resistor R by 2 connected to Vx. Okay. So previously I did the analysis assuming that no current was flowing this way, but the common mode voltage at the output of the transmitter very much depends on Vx. Okay. So let's say this current is some I tail. Okay, that represents the total current in the transmitter. If you have an equalizer, you will have multiple differential pairs, and it represents the sum of all of them. So we have V out minus Vx divided by R by 2 will be equal to VDD minus V naught divided by R by 2 minus I tail. Okay. So it's very easy to solve for V naught, but the bottom line is, if Vx keeps on dropping, V naught will also keep on dropping. This is V naught is the output common mode level. Okay. So if Vx keeps dropping, V naught keeps dropping. Is that easy to see? Because I have used equal resistances, it's quite simple. So VDD plus Vx minus I tail R by 2 divided by 2. So by changing Vx, I will affect the output common mode voltage of the transmitter. Vx is the receiver terminating voltage, affects transmit output voltage. So what would you want Vx to be? Can it be 0? Huh? Ideally the output voltage, but the output voltage itself depends on Vx. See, there are various choices. So I am just giving you, there are various ways of connecting this. Okay, like what would you do? And also I don't want, see, one of the things is I don't want my transmitter to go all over the place in its bias point when something changes in the receiver. Do we really need to transmit VOCM? No. So one thing is, if we use AC coupling, with the AC coupling capacitors can be either on the transmit side or the receive side, then Vx will certainly not affect the transmit output common mode voltage. Okay, that is one thing. What else can you do? Put the load resistor, this one, here. No, but you want a doubly terminated transmission line. I have not explained transmission lines and why we need all that, but I want termination to the transmission line on both sides. Huh? What? Where do you get that? Also, VCVS, like where is the controlling node and where is the control node? Yeah. And? To feed it as Vx. Yeah, see, one thing is, this is the transmitter and this is the receiver, so I could. Then? Huh? It is already fed to the transmission line. It is going through the transmission line. So fine, okay, you use transformer or a capacitor. Essentially the idea is AC coupling, right? Okay, that also works. What else can you do? If I gave you, let's say you had to connect it somewhere, so to some value of Vx, what would you connect it to? Yeah, one thing is to try and find out the exact common mode voltage and try and do that. Or what else? No, I didn't, not necessarily, that's not the case. No, the output common mode does not depend on the input bits. No, see, the output common mode is just this part, right? This has nothing to do with the input bits. It's independent of the input bits. Only the differential waveform depends on the input bits. Okay. So here it's not like there is one particular answer that you use always. In fact, in practice also there are many choices. I am just asking you to give some choices and evaluate it. Okay. One is, of course, you do AC coupling, then you completely make the receiver DC picture independent of, transmitter DC picture independent of what happens in the receiver. So that is fine. There are some disadvantages to that. We will discuss it soon. But one thing is, okay, let's say I want to transmit very low frequencies. In that case, AC coupling may become difficult because you have to use very large high impedance after the. So basically you are saying you will, instead of the voltage source, you will do this. Okay. Is this the, in the, oh okay, so you mean this is not ground, this is something else, or you have a resistance here. Okay, what will that do? Yeah, that's true. Essentially this is like you terminate it, but then the Vx will not significantly affect the output voltage if R high is much more than R. Is that clear? So here I took V0 minus Vx by R by 2. So here I should have to take R by 2 plus R high. Okay. So the weightage for Vx would become much smaller in that case. Yeah, that is one possibility. And what else? Where else can you connect it to? Yeah, imagine a similar circuit, right? This has on this side you have some circuit operating from a certain supply, and on the other side you have some circuit operating from the same supplies. Can you connect it to VDD on this side? Can you connect it to VDD or not? So what will be the effect of that? So it will be good or bad for the transmitter to connect it to VDD. So there are various choices. You do AC coupling, and once you do AC coupling, on this side you can connect it to anything you want. Okay. It won't affect the transmitter. This is VDD. Okay. And let's assume equal termination. So it is. So the other thing is, okay, I don't do AC coupling, I do DC coupling, but then here I connect it to exactly VDD minus I0 R by 2. So that is another scenario. So alternatively, I can also do connect this and tie it to VDD on this side. Essentially that does it. And also, okay, the last one is, so I'll show it here. So in this case, you, let's say, leave it open. I mean, that is like the high impedance. An extreme case of high impedance is you just leave it open. Okay. or you can show a very high R high, in which case you can intuitively see that it can be connected to any Vx, because Vx will not affect the output voltage. Of course, this I am talking about again DC coupled case. Okay. So this is AC coupled, and then this is DC coupled with the right common mode, this is DC coupled to VDD, and this is DC coupled but with a high impedance. Okay. The common mode, this means that the common mode impedance is very high, right? It is R plus R high, R by 2 plus R high. Okay. So all of this is possible, all of this is valid, and all of this is probably used in some case or the other. So what does it mean for the transmitter in each of these cases? What is the best for the transmitter? Second one. Why? Okay, firstly, yeah, but that is true of not just the second one. If I call this 1, 2, 3, 4, first one has some low frequency limitation. You have to have this capacitance large enough to transmit the lowest frequency of interest. Okay. So what the lowest frequency of interest, and that we'll see, right? But the capacitance has to be large, that we know. And again, we are talking about broadband signals, right? Our signals extend all the way to DC. Okay. So, but 2, 3, 4, all of them transmit DC. What else? What else can be a problem? No, but where is the, it will end up pushing more current into this. Power consumption increases with this, with 3 in the second case. Why is that? So it will increase or it will not increase? What is the power consumption in all these cases? What is the power consumption in case 1? Just this circuit. Let me call this I-tail. Huh? VDD into I-tail. In case 2? VDD into I-tail. In the third case? What is the power dissipation in the third case? No, whatever it is, what's the total power consumption? VDD into I-tail. Because the total current flowing out of VDD is the same thing that total current flowing out of VDD is the same thing that is flowing into ground, and that is I-tail. So the power consumption is the same in all cases. It is just VDD times I-tail. Okay, once you have a current source here, that determines the current that is flowing. Okay. So there is nothing to choose as far as power consumption is concerned. So one thing that we have identified is whether you want to transmit very low frequency signals or not. If that's the case, the first alternative can be more and more painful, meaning you have to use larger and larger capacitors. Okay. And especially if you are making a chip, you can't have very large capacitor on chip. How much, what is the value of capacitance you need to use in this case? So let's say, for now, firstly, I will say that some F low, some low frequency F low is of interest to me. What is the value of capacitance I need to use? C should be larger than something, but what is that something? So it's actually, if you look at this, you have R and R in series, so it is 2RC must be much greater than 1 over 2 pi F low. Okay. And these R values are typically small, because here we are talking about terminating transmission lines. So what's a typical R value? 50 ohms, 25 ohms. Why 25? Yeah, usually it's 50 ohms, but anyway, in any case, what is the highest value of transmission line impedance you can have? Huh? 377 ohms. Is that correct? Is that the highest impedance that's possible for a transmission line? 600 ohms. So anyway, it's going to be of the order of 100 ohms. It can't be very large. Okay. So the capacitance has to become quite large. So that is one thing that, in fact, doesn't favor this. The factor that favors the first circuit is that that receiver's design is completely independent of the transmitter. You don't have to rely on something happening in the receiver for the transmitter to work properly. Okay. What about the others? So should we use the others or should we not use any of them? Okay, let's even not compare it to 1. Let's compare 2, 3, 4. Which is the best? Swing in case 2 will be more than more in second than in third, or than in the first one? Than in third. Why is that? Is it? What is the swing? What is the signal swing in each case? So let's imagine that this is, let's forget equalizer and everything. Let's say that this is a differential pair that is switching from one side to the other. What is the output signal swing that you get in each case? The peak to peak swing. Huh? 2 times I tail R? In the first case. No, I am talking about swinging at. No, why is it not in the first case? Why is it different in the first case and not in the other cases? Swing, I am talking about swing. What is the swing in each of these cases? You can imagine this differential pair to be a switch. So these 2 currents will be alternately I tail. What will be the swing that you see here? Differentially at the output of the transmitter, or 2 I tail R, peak to peak. Why do you get 2 I tail R? It's only I tail R, right? The peak to peak swing is, differential peak to peak swing is I tail times R. Is that okay or not? Why? No, plus I tail R by 2 or minus I tail R by 2, right? You have the loading on this side also. So this R is in parallel with this in all the cases. Okay? The differentially it's always in parallel with this part. So you have half the effective resistance. Okay? This is what we were talking about the other day. If you have a parallel, if you have a current source driving a transmission line, the current source has to have twice the current that you actually see at the receiver. Okay? So the peak to peak swing is I tail R in all the cases. So it won't that is not the, in fact it should be, right? When we are comparing transmitters, we should be comparing transmitters that provide equal swing. So at least now we know that all transmitters provide the same signal swing. The comparison will be on some other basis. Like for instance, for first one we already identified some points that the DC bias is independent of the receiver, but you may need large C values. What about the rest? Like what's the difference between 2, 3, 4, or is there no difference at all? The common mode voltage will be different. So which one gives you the best case for design? Second one has the same common mode as the first one. What about the third one? What about the fourth one? Fourth one will be best. Compared to 1 and 2, the swing in 4 will be different. Firstly, I think we identified too many different things. One is, like someone said, this is, in this case, the common mode voltage will be same as here. Are we all in agreement on that? Because in fact, we find the common mode here and then apply it here. Okay, that was the idea. That's how we got this value in the first place. Okay, and here he is saying it is, why is this better? Because this is independent of the receiver. Is that what you said? Or so in this case, the output common mode of the transmitter is independent of the receiver. Okay, that virtue is there here as well as here. Okay, isn't it? If the resistance is very large, then Vx cannot possibly affect the output common mode. But what you said was what the swing in 4 and 1 are different. Why? No, we are not. This is a differential transmission line. Okay. So the differential termination is the same in every case. So the common mode impedance is different, but the current flowing differentially will be the same in all the cases. So the swing will also be the same. Again, would we want the output common mode voltage of the so the swing is the same in all cases, right? So there is nothing to distinguish. So we are comparing identical transmitters that drive identical signals. Okay, so the distinction will come in other aspects. So one aspect could be the common mode voltage. What is the common mode voltage in the 4 cases? And which one would you choose if you had to design the transmitter? What is it? VDD minus I tail R by 4. In every other case, it is this by 2. Okay. So does it say something? So this is for 1, 2 and 4. This is for the third case. So between these two, which one would you choose? Third one. Why? Yeah, simply because it will give you a larger, it won't saturate the transistors, right? You want if you have the common mode voltage high, it will not saturate the transistors. So either you can accommodate a larger swing or you can do something of that sort. Okay. Is this clear or no? So there is a lower limit on the output common mode voltage of the transmitter. That is because you don't want the transistors to go into triode region. Okay. Now, if a topology gives you the highest possible, the topology that gives you the highest possible output common mode voltage is the one that you want to choose from this point of view. Maybe it is not good from other points of view. Okay. So this gives you the highest common mode voltage, and all of them are driving the same swing. That is that of course it's important to keep that constant. If you have one transmitter driving 1 volt, other one driving 2 volts, it is more difficult to design the 2 volt transmitter. But here that's not what we are talking about. Here we are talking about 4 transmitters, all of which can drive, let's say, 1 volt peak to peak. But then one of them has a higher common mode voltage than the others. So that is easier to design, isn't it? Is that convincing, or does it need more explanation? So you are driving the same signal in all the cases, but the common mode voltage here is the highest. Okay. So it's easiest to keep this in saturation. Okay. So let's say you wanted to increase the swing. Now maybe all these 1, 2 and 4 are on the verge of triode region. Okay. You design it for a certain swing, and then if you increase it any further, the transistors will go into triode region. Then you go to topology number 3, then it will definitely be well in the saturation region. Then you can further increase the current high tail and increase the swing if you want to. Okay. All of them are driving the same swing, and this has the highest common mode voltage. Alternatively, if you adjust all of them to the same common mode voltage, you can have a much larger high tail here. Okay, think about what else might